All right. Okay. So the outline is the lecture is going to go as follows. So we'll discuss the limitations of conventional electronics, and once we look at the limitations, then we'll highlight how some of those limitations can be overcome by organic semiconductors. Okay, and then talk about some of the prominent applications that this particular field is enabling, and and then a little bit on the course structure. Okay, so in order to appreciate organic electronics, let's very quickly look at how electronics has evolved here. And I'm going to put this particular slide before you, which tells you how electronics evolved. And all of you know that electronics started with the invention of the vacuum diode and vacuum triode here. So that's what you see over here, right? Before that, you had motors, generators, and telephone and telegraph, but you didn't have electronics. Electronics started with the invention of the diode and the vacuum diode and vacuum triode here. And next to it is an example of what you could do with the triode. So this is an example of an early computer. And this computer that you see here, the whole thing is a computer. The whole room is a computer. Okay, I'll give you more details about this particular one. The computer is ENIAC. As around 1945, 1946. Then, of course, you know that the next major milestone in the evolution of electronics was the invention of the transistor. And that was close to the end of 1947. And this is the kind of things that one could do with the transistor. You know, the early computer that you see here, one could make, this is an example of an early calculator. And you can see that the calculator occupies, it is a fairly large calculator, occupies a sizable fraction of the table that you see here. And then, of course, the next major milestone was the invention of the integrated circuit. And that invention then has led to drastic miniaturization and drastic increase in the integration of elements. And the consequence of that is all the products that you're familiar with, cell phones and laptops and all the portable and other products that you're familiar with here. So the point that I'm trying to emphasize through this particular slide is that when you look at the evolution of electronics, what you should see is that the level of integration. What do I mean by integration? The number of components that you can integrate, the number of transistors, resistors, capacitors, or diodes, or whatever, the number of components that you can integrate and make a system. That level of integration has steadily increased. With the triode, you could see that. Let me see. So if you look at the triode had all the properties that you're familiar with that a transistor has. Okay, I mean, transistor can amplify and triode can amplify too. Using a transistor, you can make your gates. Using a triode, you can make gates as well. So in principle, the triode is very similar to a transistor. In fact, the transistor arose. The invention of the transistor happened because people were looking for a solid state version of a triode. Okay, so a replacement for a triode. Yeah. So as you can see here, a triode you could build, you could do electronics, but it was not easy. And this whole you can see that this early computer occupied an entire room, contained, but the integration level was high for that time, but not too high. All that you're seeing is 17,000 vacuum tubes. But then, along with that, 70,000 resistors, 10,000 capacitors, and all that here. Vacuum electronics had, as I said, it started in 1904, vacuum electronics, with the invention of vacuum tube. So vacuum tube-based electronics had evolved and had reached this kind of a complexity that you see here. 17,000 vacuum tubes and so many capacitors and relays and all of that. And the problems you can see here, that this kind of an integration occupied an entire room. It weighed 30 tons and it consumed 160 kilowatts of power, and it was not very reliable. As it says here, 19,000 vacuum tubes had to be replaced in 1 year alone, with an average of 50 tubes a day. So they would burn out. And 50 tubes had to be, you have to go and isolate those faults, which tubes have burnt and all of that. And then 50 tubes per day on an average had to be replaced. So you could see the problem with the vacuum tubes here. And you can see the kind of integration level. 17,000, you're all familiar now. We have millions of transistors all in a small chip. So you can see that the integration level, the ability to do electronics using vacuum tubes was limited. One can't make very complex things without getting into size and weight and power problem and reliability problems here. Okay, so that was the trouble with the vacuum tubes here. Transistor, these are the three people who invented the transistor here. Anybody recognizes? Okay, which one is Bardeen? No, the next question. Out of the three that you see here, anybody? Huh? Who's the one sitting there? Shockley, that everybody knows. Okay, and who is this person? Bardeen, and then this one is Brattain here. And who are the guys who invented the transistor? Huh? Bardeen? Bardeen. So some of you know, you can go and YouTube has a lot of videos on the history of invention of the transistor. These are the two guys actually who invented the point contact transistor. The first transistor, in fact, the first patent on the transistor is by these two guys only, Bardeen and Brattain here. Now, Shockley was the leader of the group. Shockley was the leader of the group, but then he was not involved in the actual invention of the first transistor here. But then very shortly afterwards, Shockley came up with the junction transistor. The earlier one was a point contact. He came up with the idea of bipolar junction transistor. And so he, if you go and read history, he was very upset that the first transistors were, he was not a part of the invention here. And subsequently, some unpleasant things happened. He was not in very good terms with the other two guys here. He was very upset. And this shows that this is one of the early photos of, which was going to go to press. And Shockley sort of set aside the other two guys and sat down, trying to take the credit. And in fact, these are the two guys who had actually invented the transistor here. So, when you read history, you see these rivalries and there are other things that come into picture here. Anyway, so that was the landmark event. I've written 1948. It was actually close to the end of. It's difficult to define when was it invented, a particular thing. So close to end of 1947, December 1947, was when it was reported in the press that the invention of the transistor here. And with the transistor, now you can see earlier what occupied an entire room now could be done and could be fitted onto a table. Okay, so you can see now, and you can see the integration level of this particular one: 530 germanium transistors, 2300 diodes, and all of that. So the point that I'm trying to make is, with the invention of the transistor, what occupied an entire room could now be fitted onto a table, and what weighed tons, right? Now still weighs kgs. Okay, and power consumption is here, and what consumed kilowatts of power now consumes 90 watts of power. So you can see now that I can integrate a lot more components and not get into the size and the weight and the power problem. Still, the size is large. You can imagine now 530 germanium transistors and 2300 diodes are occupying a tabletop, right? And then suppose you have to integrate 10,000 or 100,000 transistors and components. You can imagine what would happen. Okay, so still integration is a problem, right? So you can't make very complex things without getting into, again, the size and the weight and other problems here. So the transistor helped a lot. It was a huge event in the evolution of electronics. But then transistor by itself is not sufficient for all the things that you see here. If without the next major invention, and which is the invention of the IC. Right, so IC, a better phrase for integrated circuit. Every circuit is in some sense an integrated circuit. You're interconnecting components. So in some sense, everything is an integrated circuit. A proper phrase for an IC is monolithic integration. Monolithic integration meaning that on one single substrate, you make all the components and you interconnect them also. Okay. That is what is meant by monolithic. The word monolithic comes from monolithos. Mono means single and lithos is like a stone, right? So which means that on one single substrate, you are making, the components are made on that particular substrate also and interconnected on that particular substrate. Now, this point is very important to understand what this monolithic integration, what the invention of the IC did. And to do that, let's look at discrete versus monolithic circuits here. The conventional circuit, for example, the circuits that you make on a breadboard, right? Or that you make on a PCB. Those are discrete circuits. Why do I call it discrete? Because they're made up of discrete components. And what are discrete components? Components that have been fabricated beforehand. You've already made those components and they've been packaged. So fabricated and packaged components you take, you bring them on a substrate, breadboard or PCB or whatever, and then you interconnect them with either printed wires, printed connects and things like that. Remember, the components have been made beforehand in a discrete circuit. They've been made beforehand. They exist as discrete entities, and then you connect them up. Okay, so that's the discrete circuit. Monolithic circuit is, on the other hand, you make the components on the substrate itself, and you interconnect them on the substrate itself. Okay, so for example, if you go and look at a discrete component like a transistor that you're well familiar with, open it out. This is a schematic representation. If you open it out, this component that you see here is of the size of a centimeter, let's say, right? A centimeter, a few millimeters by few millimeter, or a centimeter. So typical size is like, let's say, a centimeter here. If you open it, if you could go inside and see, what you would find is a small piece of silicon here, and this piece of silicon is there inside this particular chamber here. And if you go and examine this particular transistor, what you would find is that the small piece of silicon that you see, let's say it's a bipolar transistor, so it has a emitter here in the center, and then the base, and then the collector, and all of that. The transistor itself is very, very small. Even the early transistors were, say 100 micron by 100 micron. Okay, so very, very small transistor here. But the trouble is, and one can make it even smaller. Okay, one can shrink the geometry and make it smaller here. The trouble is that even though the transistor is very small, how do you make a circuit out of it? How do you connect two transistors? If your method of making circuits is that you have to hold a component in hand and another component, and then you have to hold the component in hand, bring it, put it into a socket, take another component with hand, put it into a socket, and then connect them up. Look at the way of fabrication. Whether you do it with hand or a machine holds a component and puts it into a PCB, the method is that you have to physically pick a component and then place it on a board, right? When you have to do that, physically pick and place, the component has to be of the order of a few centimeters or so. So even though the transistor is very small, I have to make it big. I have to deliberately make it big in order to handle it, because my method of fabrication is such that I have to pick it and then place it and then interconnect. So I have to make it big. And how do you make it big? Well, you make it big by attaching all these pads that are there. Every transistor, every IC is surrounded by a metal pads. And metal pads, and what you do is, now you can see here, this is a big metal pad, is nothing like a big piece of metal here, big piece of metal here. And then to these pieces of metal, you attach wires, very fine wires, wires here. And these wires then are attached to the pins here. So now, even though the transistor is very small in microns, but you have to make it into the size of a centimeter. And therefore, why? Because of my way of manufacturing. The way I manufacture is by holding and putting it on a substrate here. So the transistor is very small, but then I have to make it, package it into a large entity, which is 1 centimeter. And then, of course, one has to place it on a board and interconnect it with other transistors that you see here, and resistors and all that. So this is an example of an early op-amp. And what you see here is a couple of transistors, resistors, and capacitors here. And this is an example of a discrete circuit, right? Each component has already been made beforehand. Resistors have been made, capacitors have been made using various processes. You could have a carbon resistor, you could have a ceramic capacitor, using different methods. All these discrete components are brought together, and then they are put on a board, and then they're connected with wires. Okay, and the wires can be printed on the board itself. Okay, so wires are there, and that's an example of a discrete circuit. Okay, now contrast that with a monolithic circuit here. This is an example of a 741 op-amp that you are all familiar with. Look at the large number of transistors here. The difference is the transistor is not made beforehand and then brought and integrated. The transistor is made on the piece of silicon. All the transistors that you see are made on this piece of silicon. All the resistors that you see are made on this piece of silicon. all the capacitors that you have. There are not too many capacitors. One here, capacitor is also made on that piece of silicon, and the interconnects are also made. So now you don't have to really take one transistor, fabricate and bring it to a substrate, hold it in your hand. It's made on the piece of silicon itself. So the whole thing then, it is basically the whole that you see here after you package is the size of a transistor itself, the packaged transistor. Okay, so remember, why was the size of the circuit becoming large? Because each individual component you had to package. So each individual component becomes a centimeter. And then you have to, if you bring in, let's say 1,000 components, each one of them is a centimeter, then you can imagine what will be the size. Okay, but then if you don't have to package each individual component and you have to package only the final thing here, then the final thing is also of the same, because the actual transistors are very, very small. 10 micron, 40 micron, 10 micron, everything is very, very small here. So this, you can see here, the difference between a discrete and a monolithic circuit here. So that led to, as you can imagine, a drastic miniaturization and a lot of improvements. Improvements in terms of reliability, improvement in terms of speed. For example, when you make a circuit like this here, when you take two transistors and you interconnect them with a wire, you can imagine if the components are of the size of a centimeter, the interconnects are also of the size of a centimeter, right? And a centimeter of line has a lot of capacitance in it. So the interconnect delays, they become, and the interconnect here is very, very short. So you get improvement in performance, you get improvement in reliability, all of those other improvements that come. And therefore, we say that for electronics to have reached where it is, the transistor, in the language of maths, you keep on talking about necessary and sufficient conditions, right? So transistor is a necessary condition for the present state of electronics, but sufficient condition is the invention of the IC. Without the IC, you won't have any of the things that you're familiar with. Okay, and so once the IC was invented, and remember what IC means, it's a new way of making circuits, new way of making and interconnecting elements here, and that's called monolithic integration here. So once the IC was invented, then electronics really took off, and electrical engineers would be familiar with Moore's law, that the integration level has been steadily doubling. This is interesting. 2003, this was a statement made by Gordon Moore that the number of transistors shipped in a year had reached 100 times the number of ants estimated in the world. Yeah. So you can see that with the invention of the IC, the whole of electronics was unleashed. And no wonder that, remember, transistor was invented towards the end of 1947. And people realized the importance of transistor very early. And 1956 was the Nobel Prize given for the invention of the transistor. The importance of integrated circuit was recognized, but in 2000, the people who invented the IC were honored again with Nobel Prize. So you can, we say how important was a particular event. Well, when it's honored by a Nobel Prize, everybody agrees that it was a big invention. Yeah. So 2000. Jack Kilby was given Nobel Prize for inventing the IC. All right. So, what are the limitations of the conventional silicon-based inorganic electronics? Well, the first thing that you would note that all these integrated circuits, all the electronic components that you're familiar with, are made on crystals, on crystalline semiconductors. Whether you take your bipolar, you take your MOSFET, you take all your ICs, they're all made on wafers of silicon, and wafer of silicon is nothing but crystalline silicon. If there are few defects in that crystalline defect, many of the circuits, many of the transistors will not work. Similarly, if I take light emitting diodes, lasers, and solar cells and others, they're also, for example, light emitting diodes may be made on gallium arsenide substrate. They're also crystalline. If they're not crystalline, none of the light emitting diodes will work. So the point that I'm trying to emphasize is conventional inorganic semiconductor are all made on crystals. If there are few defects, or if the material becomes non-crystalline, none of those devices will work. Your bipolar transistors, your PN junction diodes, none of them will work properly. So the material has to be crystalline. Not only that, has to be a very, very good crystalline with very few defects. Okay. The other thing is the process for making those devices involve usually very high temperature steps here. For example, let's take a MOSFET. In a MOSFET, for example, I have to do a silicon dioxide. Silicon dioxide is grown at very high temperatures. Then to create a source and drain, I have to do, let's say, N plus regions here. You may do implantation, but after implantation, you know that there is damage and you have to anneal. Annealing is done at high temperature. So the point that I'm trying to emphasize is that a number of high temperature processing steps are required in order to create the transistors and other devices here. So 2 points that I'm trying to make is that you require crystalline materials, and you require high temperature processing steps. Okay, which means the following. Which means that monolithic integration. Okay, which means ICs. I cannot make ICs on other substrates such as glass, plastic, etc. Now, what do I mean? I'm saying that I cannot do monolithic integration. I cannot make an IC on glass or plastic. I can only make IC on silicon. Why? Because let's say I'm talking about a silicon bipolar transistor, right? Now, I can take silicon and deposit it on glass. Two things will happen. When you take silicon and deposit it on glass, it's no longer crystalline. You have to grow the silicon crystals, right? And if you deposit it on glass, it becomes amorphous. And therefore, my bipolar transistor will not work. So the materials, they tend to become amorphous on glass. The other thing is, or on plastic. The other thing is, to make those transistors, I require high temperature steps here. The glass will melt, the glass will melt, under 500 degrees Celsius. The plastics will melt under 200 degree or even 150 degrees Celsius here. So which means that the conventional electronics, conventional ICs, I can't make. I can't do monolithic integration on glass or plastic or even paper or cloth. Okay, what do I mean by monolithic integration? Again, making the components on a piece of cloth and interconnecting them. Now you may be wondering, why do I want to make an IC on plastic? What for? And why do I want to make a IC on cloth or IC on paper? Why can't I just make, let's say, IC on normal IC and put it on cloth? Why can't I make components and put it on cloth, or make components and put it on plastic? Why can't I do that? But remember what that means. If you make components separately and then put it on glass, what does it mean? You're making a discrete circuit, right? While if you make the component on the substrate itself, you're doing monolithic integration. And we know the differences between the two. Discrete means your integration level is very limited. A few components itself will make the size large, while monolithic means it's very, very small here. So that's why I've already talked about the differences between monolithic and discrete. So the point is, which means that if I want to make circuits on other substrates, then I'm forced to, using inorganic, I'm forced to do a discrete kind of a circuit. And discrete circuit means integration level will be very limited. Integration level being very limited means the complexity of system that I can build is very limited. And therefore, I can't do complex things. I can only do very, very simple things. And this point I would like to illustrate through the example of a light emitting diode. Okay, light emitting diode was invented. Actually, the first report of light emitting diode was very early, in 1876 or so. Very early, in the sense that people saw emission of light when you pass current. Okay, the phenomena was seen, but a practical LED was invented in 1962. Okay, LED was invented in 1962, and now imagine that if you want to make a display on which you're familiar with LCDs and other, you want to make a display on which you want to show images and other things here. And so imagine that you have an LED, right? You have an LED and you can turn the LED on or off. And so LED is like a pixel, right? You can make red LED, green LED, blue LED, and you have a pixel. And therefore, suppose you can make an array of LEDs, right? Array of LEDs, let's say on glass or whatever substrate. You can make an array of LEDs, and then depending on which LED you turn on or which LED you turn off, you can display an image. If you have a high density of LEDs, you can display an image. So you can make a display using LEDs. And LEDs are very nice potentially for making a display, because LED watt set, all of you know at what? 1.5, 2 volts is all that you have to apply. They're very efficient, right? So why not make a display using an LED? Well, you find that LED was invented in 1962, but its impact on displays has been minimal. You don't find any displays. The only displays that you find using LEDs are the 7-segment displays that you're familiar with. And well, if you can call this a display, traffic lights, increasingly traffic lights are being replaced by LED. Well, it's maybe a 1-bit display, right? On or off. That's all that you get here. This is all of you here of LED TVs and all of that. They are not really, the display is not made up of LEDs. The display is still LCD. This laptop also has an LED display. The only thing is, behind the LCD, you need a source of light, and the source of light is an LED, right? So it's just being used as a bulb. The display is still liquid crystal displays, LCD. So what you find is that LEDs were invented in 1962. And I would think if I have a nice source of light which I can turn on or off electrically, then I can make an array and very nicely make an LED based display. But you don't find any LED display except for these giant displays. This whole wall is a display. Sometimes in these stadiums you find a huge display, right? Some of them are LED displays. Okay, so except for that, otherwise you don't find any LED based displays at all. Now, what is the reason? The reason is as follows: that I have red, green, blue LEDs became common only lately in 1990s here. So I have red, green, and blue LEDs, but I can't make these red, green, and blue LEDs on an inexpensive substrate such as glass. I've already talked, because note that if you want to make a display, right, and if you want to put it on a cell phone display, then you have to make it on glass. Well, you may be thinking, well, why not I make it on semiconductor? 2 reasons. One is, whatever semiconductor you think of is far more expensive than glass, right? So your display will become very, very expensive. The other thing is, choose any semiconductor that you want, right? Now, a semiconductor, choose, let's say, a gallium arsenide substrate, right? It's a semiconductor. It's very expensive. But on this gallium arsenide substrate, I can grow, let's say, a red LED. Okay, I can have all these different layers and I can make a red LED. But remember, a green or a blue LED requires a different semiconductor, because the light depends on the energy gap and requires a different semiconductor. Different semiconductor means different lattice constant, different crystalline structure. So now if I require a gallium nitride for blue LED and gallium arsenide is the substrate. Now if I put gallium nitride on gallium arsenide, what happens? There's a lattice mismatch. And therefore gallium nitride that I get is no longer crystalline. And therefore the blue LED will not work. So I can't find a common substrate on which I can make a red and a green and a blue LED simultaneously. First of all, I can't do it on glass, very cheap substrate, because the materials become amorphous and none of them will emit light. Secondly, if I use a crystalline substrate, I can use either gallium arsenide or gallium nitride or whatever. Red may work and green, blue may not work. So I can't simultaneously make red, green, and blue LEDs on any substrate that you have. Well, people are trying, for example, on a common, let's say, silicon substrate through various means. Maybe you can grow gallium arsenide in one place and gallium nitride, but so far there hasn't been success where you can do that. So 2 things: one is very expensive. The other thing is I don't have a substrate available on which I can make all 3 different LEDs. Why is it that I can't do that? Because I require crystalline. Look at the reasons why I'm not able to do it. Because I require crystalline semiconductors. And they require lattice matching. So that's the reason why I can't make red, green, and blue LEDs on any common substrate. I can't do that. And therefore, I can't make a display. Now, you may be thinking, well, what about a discrete display? I make a red LED using gallium arsenide, blue LED using something else. I make them. And then I take them and bring them and I integrate them on glass. Why don't I do that? Right? But that would be a discrete way of making it. What is the problem? Let me illustrate it to you what the problem is. You can see why. Look at this example of a discrete display. Each one of them is an LED. Now, discrete display meaning each LED is, you will have to package in some sense, and you will have to, so each LED is like a centimeter, right? And the separation between LEDs is of the order of like a centimeter. So you can see this array of LEDs. It's a display, but then, sizes and separations and all of that are of the order of a centimeter. We call it a dot pitch. A pixel pitch is of the order of a centimeter. Is that good enough? Well, let's see. This is an old display. 2.4 inch. This was state of the art, several years ago. 2.4 inch is a Nokia phone here. Active matrix display. Forget about the word active right now. 320 into 240 pixel resolution, which means what? Rows and columns, right? And so if you, based on how many pixels you are, remember each pixel has to be an LED. You can calculate using aspect ratio, which is given here, and you can calculate that the pitch required is 0.05 millimeter. For this display that you see here, 2.4, for this kind of a resolution, the pixel pitch, each pixel separated from the other pixel has to be 0.05 millimeter. That's the kind of density that you want of those pixels. You can't achieve this particular density through a discrete way of making things. Discrete circuits will not give you this kind of a density at all. And the only way you can get this density is by actually making things on the substrate itself, which means through monolithic integration. So, we are not talking about 1,000 rows and 1,000 rows by 1,000 rows or so. So we're talking about much more complex displays than this, and then the pitch will become even smaller. So what it is illustrating is that to make a display, I require a density of integration, which cannot be achieved through discrete methods. The only way you can achieve it through monolithic. And so now you see why we don't have displays made out of LEDs. The reason is I can't make those red, green, and blue LEDs on glass on a cheap substrate or any common substrate. That's the first problem. If I go to a discrete way of making things, then the pitch becomes very, I can't achieve this kind of a pitch. So now you will appreciate why I can make these giant displays here. Now, when I have a giant display, now there, when I work out these numbers that you see here, these numbers which are 0.05 millimeter, that's because it is 2.4 inch. Now, when I have several meters by several meters, then the pitch becomes large, and therefore then I can do a discrete. Then I can go ahead and make a discrete display here. So when you go to those giant, huge, the whole wall is a display, you can go ahead and build using LEDs, and people do that. But then for reasonable size LEDs, reasonable size displays, that's not possible. You have to do monolithic integration. So here is an example that you are seeing that, when I made a statement, I can't make ICs on glass or plastic. And immediately thought came to your mind, why would you want to make an IC on glass or plastic? Well, this display is an IC. Display is an IC. I want to make an IC. IC means what? Integrated circuit. You're integrating components monolithically. Well, I want to make an IC on glass. Then I can make a display. A display is nothing but an IC, right? So I would like to make an IC on glass, and therefore I will have a display made out of LEDs. Not only that, if I could integrate my LEDs on plastic, right? I could make an IC with LEDs as components on plastic. Then I could have flexible, very lightweight displays here. You can see all the advantages that are there. But I can't do that using inorganic semiconductors. Why? Two reasons. Why is that? Because they're crystalline. They work when the material has to be crystalline. And second, they require high temperature processing. Both these reasons prevent me from doing things on plastic or paper and things like that. I can't do monolithic integration. Okay, so that brings us to organic now. So here is an example of an inorganic LED. Oh, there's a big mismatch between the colors on this laptop and the colors. There's an old projector. So this color is actually on my screen green, and that's looking like a yellow. All right. Anyway, but so this is the conventional inorganic LED, and which is made on a gallium arsenide substrate. You see here, all the layers are crystalline, right? Stacks are crystalline here. This is an example of an organic LED. Now let's start noting the differences here. The substrate is glass, and I've written here ITO coated glass. ITO, the full stands for indium tin oxide. Indium tin oxide. So it is a conductor. It's actually like a semiconductor, but is doped heavily. So it's like a conductor, but it's transparent. Okay, so the glass is coated with a transparent conductor, which acts as a, LED has two terminals, anode and cathode, right? So it acts as an anode. And just schematically, I'm showing one connection here. Okay, so the glass is coated with very thin layer of indium tin oxide, which is a transparent conductor. Okay, then on top of that, I'm showing you two organic layers. One can have more organic, just like you have a series of semiconductor layers here, two organic layers. Both these layers are amorphous. They are no longer crystalline. They're amorphous semiconductors here. It belongs to the amine family. This is ALQ3 here. Both these layers are amorphous. Amorphous means there's no order, right? Long range order, there's no order here. And therefore, I can easily deposit it on glass. What happens when you take a material and you deposit it in glass? It becomes amorphous. There's no order, right? So it's an amorphous material. And remember, another thing with amorphous material is you can take one amorphous material, put another amorphous material on top of it. There's no lattice mismatch. None of those issues actually come. You can deposit on top. So both of these are amorphous materials. And on top of that, one is put a electrode magnesium with magnesium alloyed with aluminum. So that's the cathode here. So now, interesting thing is these materials, these active materials, these are semiconductors. They're amorphous. When I apply voltage between these two electrodes, a current flows and it emits light. That's the interesting part of these organic materials here. My organic material, my inorganic gallium arsenide, if I put it on glass, it becomes amorphous. It's not going to emit light. I can't make. While these organic materials, they emit light. Now, why are they emitting light? That's what we'll see as part of this course. The light emission, as all of you know, molecules do emit light. If you excite a molecule, it gets into an excited state and then it falls back and it emits light. So that's what is happening. When I pass current, my molecules here, they go into an excited state and then they return back. And so the properties of these materials are not so much determined by the crystalline or long range order. They're determined by the nature of the molecule. I can have one molecule and it will emit green light, and I can have a different, all of you, if you remember organic chemistry from your 12th or 11th, the chapters used to be very long and so many different molecules are there. In fact, there's a whole wide variety of molecules that are there, right? There's an endless. In fact, you tell a chemist and he'll invent a new molecule and give it to you within a week. Attach one chain here, attach something else here. So there's a wide variety of molecules that you can get here. And so the point is that all these layers are amorphous. And I'll show you that you can deposit them at very, very low temperatures. That's why you can see here, I can make this on glass. Okay. So now I can have one series of layers for red LED, another series of amorphous materials for green, another series of materials for blue. No lattice matching, and none of those requirements are there. All I have to find is a molecule which can emit red light, molecule which can emit green light, another molecule which can emit blue light. And I take those molecules, I take those organic materials, deposit them here, here, here. I bias them, and then I can get a red, green, and blue LED side by side, and I can make a nice display. And remember, the LED is being made on glass. It's not that I'm making it separately and then bringing it on glass. No, so I start with ITO coated glass. I deposit this material. I make this electrode. So the whole thing is being made on glass, right? And using masking and other ways. On one place, I deposit these materials. I get red LED. On another place, I deposit these materials. I get green. Selectively, I make the deposition. And therefore, I'm making all these LEDs side by side. It's not that I'm bringing them and interconnecting them. And the interconnects are also made on this also. All right, so I can make this complete display on glass. And this is an example of an early organic LED based displays. And all of you know now, many of these cell phones, especially from Samsung and LG, the higher end phones are all active matrix LED phones here. So OLED phones are there. OLED displays are there in the commercial arena. TVs are also there now. Okay, so what you can see is that there were things that I couldn't do with inorganic. I had a very nice inorganic LED in 1962, but I couldn't make a display. And this organic LED then came in using amorphous materials, and very quickly one could make displays here. Okay, and the other thing is also remember that people could make green and say red and orange and green LEDs early on, 1960s. Blue LED, they had to really struggle. The reason being is that blue LED, you require a larger band gap, and gallium nitride was the preferred material, and people were really struggling with growing good quality gallium nitride crystals and crystals and doping them and all that. And this year's Nobel Prize went to the invention of blue LED. So they were really struggling with it. One of the reasons was, well, you have a handful of material. You don't have too many semiconductors. This one here, gallium nitride. Say, you have a gallium nitride and you find it's difficult to grow dislocation free and high quality gallium nitride crystals and dope it and all that. Well, if one material is giving you a problem, go to another. Try another material, try the third or the fourth or the fifth or the sixth or whatever. Why didn't they do it? You don't have any choices, right? Now here, you see the people came up with green LED, and in no time they had a blue LED. In fact, there's an unlimited variety of semiconductors that I have available here. I mean, organic molecules, as I said, you can, I'll just give you examples. So the properties of semiconductors, organic semiconductors, is significantly determined by the organic molecule that you're using. And there's a great freedom in altering the semiconductor's property through modification in molecular structure. Just as an example, look at this. This is a polymer. When you put a bracket and you show a molecule, what you're saying is that this repeats itself, right? And repeats itself maybe 1,000, 10,000, 100,000 times here. So it's a giant molecule, and macromolecule, we call it polymer. So here is an example of a polymer called PPV. You can see the chain here. And when you measure something like a conduction band and valence band, you see that the electron affinity is 2.73 electron volts. And the ionization potential, which means 5.2. The energy of this level is 5.2. The energy of this level is 2.73. You could think of it like a conduction band, valence band, and the gap as energy gap here, right? Now, look at that same molecule, and a methyl group has been attached, right? What happened to 2.73 became 2.65. What happened to 5.2 became 4.72. Look at the energy levels by attaching a methyl group here. Attaching something else, look at the changes here. This went to 5.5. Look at this, 3.6. So what I'm just trying to illustrate, attaching a group here, attaching something more here. Look at the freedom with which you can alter the energy levels. You can move this up, down. You can move this up and down. So thereby you can get a red, green, blue without any problems. In fact, there are almost like unlimited variety of organic semiconductors that you can use. This level that you see 2.7, I can make it 4. This that you see 5.2, I can make it 6.2. So these energy levels you can play around, by taking a molecule, by attaching something to it, you can play around with it. Okay, play around with these particular levels and get a wide variety of organic semiconductors. So that's what I'm saying. There's a great freedom in altering these semiconductors' properties. That freedom in inorganic semiconductors, you have some freedom, but very, very limited as compared to the amount of freedom that you have here. Okay. So band gaps that you can see here, energy gaps 2.47 eV, 2 eV, 1.9 eV. You can get all these by simple modifications here. The other one is these organic semiconductors that you see here. We call them molecular solids, in which molecules are held together by van der Waals forces. If you take an organic molecule like I talked about here, say take this particular molecule, AlQ3. Okay, I'll show a structure later on. So AlQ3 is a molecule, and the molecule within molecule, the bonds are covalent bonds and all that, and they're very strong, right? So the molecule is fairly stable, but one molecule is bonded to the other molecule by very weak van der Waals forces. Okay, very weak van der Waals. So they are solids. For example, AlQ3. You can see it as in a form of a powder, and it's a solid which is there. But remember, a solid is there, but one molecule is bonded to the next by very weak forces. What does it mean? That if I heat it up at very low temperatures, it vaporizes. Just 150 degrees Celsius or whatever, it just vaporizes. So you compare that, silicon will melt at 1400 degrees Celsius. Okay, then you can, if you're making a semiconductor device, you have to make a film of semiconductor. So now you can see how very easily I can make a film of semiconductor. What I can do is I can take a crucible, put some AlQ3 material in it, right? And I have a substrate on top. You guys will be doing the lab also. So I have a substrate on top, and then you heat the crucible to 150 degrees Celsius, right? And you have a sample at the top. And as you heat it up, it vaporizes. And if the chamber is evacuated, then these molecules which come out, they come out with a little bit of energy. So they'll just straight away travel to the substrate. Substrate is cold, and they go and stick to it, right? And they go and stick to it. And you do that. You do this evaporation, thermal evaporation for say half an hour or whatever, and then you form a nice film of organic semiconductor. And you can get a film which is 50 nanometer, 100 nanometer, 150 nanometer films. So the films that we talk about are very narrow. We are not talking about here bulk crystals which are 300 micron. We are talking about this whole organic electronics. Another name for it could be thin film electronics. All the films that we form are all thin films. Okay, nanometer, 100 nanometer typical dimension. So very nicely, I can form a thin layer of organic semiconductor by simply taking a crucible, heating it up, and it goes and then sticks, and I form a film. Of course, I'm making it very easy to get high quality films. You have to optimize the condition, the growth rate, deposition rate, and all of that. So that is there. But the process is very simple. Okay. So there's one class of organic materials, which are these molecular solids, which you can vaporize very easily. There's another class which I just showed you, which are polymers. Now, polymers are soluble in these solvents, chloroform, xylene, and chlorobenzene, and there are solvents like this. So they're soluble. So what you do is you can form a film by another process which we call a spin coating. So what you do is in spin coating, you make a solution, and you have your glass substrate, and you put drops of those solution on the glass substrate, and then you have a spinner, right? And then you place the glass substrate on that spinner, and it's held through a vacuum to this, to the spinner, and then you rotate it at 3000 RPM. And as you rotate it, what happens is the liquid all spreads over and evaporates, and you again form a very thin layer of organic semiconductor. You can get 50 nanometer, 100 nanometers of fairly uniform on a large glass plate, fairly uniform 100 nanometer films of this particular polymer here. So look at that. You formed a film of organic semiconductor on glass by what? Very simple method of spin coating. Taking a solution, dropping it, spin coating it, and then you have a film. And after that, you can give it some heat treatment, annealing, and all of that you can do. But you have a layer of organic semiconductor formed very easily, right? And so you can do that. So you can see that the methods of fabrication are very, very simple. And I can do it either through vaporization route, or I can do it through spin coating route here. So let me summarize the advantages of organic semiconductors. Because organic semiconductors need not be crystalline. Well, you can make it crystalline, but they need not be crystalline. Because they can be deposited at very low temperatures. Organic devices such as LEDs of different colors, solar cells, transistors, all made of different semiconductors, can be monolithically integrated on not only inexpensive glass, but plastic, paper, fabric, anything that you can think of. I can now make transistors, LEDs, solar cells on anything that you tell me. Glass, I'll make it. Plastic, I'll make it. Paper, people are making it. Solar cells on paper, transistors on paper. All right. So any cloth, people are making it. So anything that you can think of. So in some sense, what this organic electronics is doing, if you take a very broad perspective, is actually liberating electronics. It's like liberating electronics in the sense that it's saying you're no longer confined to crystalline substrate. You can do electronics. You can make integrated circuits on anything that you want, right? And so that's what I like to call it. You can now make monolithically integrated circuits on any substrate. You can make it on this table. You can make it on wall. You can anything that you think of, you can make it. Right? So this is the new world that this organic electronics is opening up. Electronics using organic materials which can be deposited at very low temperatures. All right, so it can allow electronics to be used in places where it has never been used before. So now people, it's up to your imagination where you want to make integrated circuits. Now you can make it on paper, but then the issue is it of value? I mean, do you have an application in mind? So that is there. It's allowing you to do that. Now you have to come up with the application where I can use it, where it makes sense. You have the capability, but then you have to think of suitable applications here. I've talked a little bit about this processing advantage. Let me explain this a little bit more. Uh, Conventional inorganic electronics, is done in ultra high clean environment that you see here. People dressed up as astronauts here because a little bit of dust and defects and all that plays havoc. And it's a fairly complicated processing. And these fabrication fab plants, they cost now upwards of billions of dollars here. And that's why you find that even very big companies have given up on fabrication. Texas Instrument used to fabricate, as I said, Jack Kilby was from Texas Instrument. He invented the IC. Texas Instrument no longer fabricates. At least they hire it. In fact, they get it made by somebody else. So fabrication has become so complex that only a few, companies can do that. Okay. And so that's conventional processing, silicon-based processing here. Now, what organic electronics is opening up a very different way of processing things here. As an example, we have in this center also inkjet printing. Okay. Now imagine that, why imagine? I'm saying this is happening. Okay. So you have a glass substrate or a plastic substrate, and you are all familiar with your inkjet printers that are there. Instead of those cartridges, instead of putting red, green, and blue ink, I put here now solutions, inks. For example, I could put a ink which is a conductive ink. Example, silver ink. What is the silver ink? Made up of silver nanoparticles. Silver nanoparticles which are dispersed in an ink form. So what you do is, this ink is there, and you put it in this cartridge, and then what you do is, just like you draw a line, right? You're printing a line, you draw a line. You draw a line here, except that this line is what? Is made up of silver. And then you give it a little bit of heat treatment, and you get a nice silver film on the piece of plastic. So there is your source, and there's your drain. 2 electrodes. Okay. Let me show you how to construct a transistor. So I have a plastic piece, and I put 2 electrodes here. This is your source and drain. Source and drains are metal, right? Okay. Next, I take my cartridge, another cartridge. You have red, green, different cartridges are there. Another cartridge I fill with a polymer which is an insulator. Remember, I'm making a MOSFET. Don't think of oxide, but think of more general MOSFET structure. All that you require is an electrode, and you require an insulator, and you require a semiconductor, right? That's all. These are the elements of a transistor. So now I have an insulator. Another cartridge filled with insulating ink, right? So this is my insulator here. So I print everywhere. My insulator. Another cartridge filled with a semiconductor ink, polymer ink. As I said, polymers you can put it in a solution form. So they are there, and you put another polymer here, right? And you put another, now here, this is my gate at the top. So another metal here. So you see here, it's an inverted transistor. Normal transistors that you see here. So you have a source and drain, and then you have, I think source and drain. So this is a semiconductor. So I said it wrong. This is a semiconductor, and then you have a insulator, and then you have a gate on top. So you have source and drain, and then you have a semiconductor on top, and then you have a insulator on top, and then you put another electrode, and then you have a complete printed transistor. So you have printed your transistor using inkjet printing here. And here is an example of this inkjet printer here, which is printing these transistors here. So this is a early picture, but people are doing it. Imagine that you have a roll-to-roll kind of a processing. I showed you inkjet printing, but you can use other printers similar to what are used for printing newspapers and magazines. Okay, called gravure printers and flexo printers and all that. So imagine I can do now and print, and I can print my circuits, right? So I can have a high-speed roller going and printing circuits, very fast, just like newspapers are printed. You can imagine how many circuits you can print in one day, right? So you can see it's opening up a very different way of making things, very different processing, printing as a technique for making all. So using printing, people have made transistors, people have made circuits, people have made LEDs, solar cells, sensors, All of those electronic components that you're familiar with, people have made full, you can imagine, loudspeakers. Printed loudspeakers are there. And of course, all of you are hearing now this push towards 3D printing, right? So 3D printers are there, and with those 3D printers, you can print. People are talking about printing whole houses and all kinds of things that are there. Yeah. So this is an example of a printing circuit. Okay. So I'm talking about lots of. My time is up, I think. So I'll just 12:30 we stop. No. Oh, we are. What is the time now? 11:30. 11:30. Okay, so I have half an hour more. Okay, so the advantages I've talked about and painting a very rosy picture of what organic electronics is. There are problems and challenges here. One of the problems that you can anticipate is that I said many of these advantages of organic semiconductors are coming because they are amorphous in nature, that you can deposit it on anything that you want here. But amorphous in nature means disorder, and disorder means poor mobility. Okay, so poor mobility, poor electron and hole mobility. So carrier mobilities are poor in these materials. Now, some of these numbers can be, I know you would say poor, but you must be wondering how poor. Okay, the mobilities that you are familiar with are mobilities of silicon. Silicon MOSFET mobility in the channel is around 500 or so, electron mobility. So the numbers that come to your mind are good mobilities of 500, 600, 1000. These are good numbers. Now, poor mobility, the number that I can give you, how poor can it become? 10 to the power minus 5. That's what I said. It's going to be shocking to all of you. 10 to the power minus 5 mobility. And now you must be wondering, what can I do with 10 to the power minus 5 mobility? Right? 10 to the power minus 3. Can you do anything with it? No? Well, that's where I think our biases come into picture. 10 to the power minus 5 mobility. Now, I can make a very nice LED, organic LED, very efficient organic LED with 10 to the power minus 5 or 10 to the power minus 4 mobility. We'll go through the numbers. You don't require. See, gallium arsenide is giving you 1000, 4000. Fine, it's giving you mobility, but you don't require. You can make very nice, that's what I said, you can make very nice gallium arsenide, organic LED with the mobility of 10 to the power minus 4 or 10 to the power minus 5. You don't require that numbers. So don't think, that's what you take a material, measures mobility, it's giving me 10 to the power minus 5, it's junk, throw it away. That's not true. You can make a nice LED using that. Fairly efficient, will give you bright light. In fact, many of those LEDs out of which their cell phones are being made, mobility would not be more than 10 to the power minus 3, 10 to the power minus 4. And there you see an application with that mobility. Solar cells, right? The solar cells are made out of silicon. Silicon gives you very high mobility. I can make a very nice solar cell with 10 to the power minus 3 or 10 to the power minus 2. Large area solar cells with 10 to the power minus 2 or 10 to the power minus 3 mobility I can make. No issues at all. Will give you power conversion efficiency of 10%. Silicon gives you high, 20%. I can make a 10% solar cells, 10% efficiency solar cells right now with a mobility of 10 to the power minus 3 or 10 to the power minus 2. I don't need, so the point that I'm trying to make is I don't need very high mobilities. For many applications, I don't need. Where is it that you require very high mobilities? And by the way, there's organic LEDs can switch at megahertz speeds with 10 to the power minus 4 mobility. Why? Because you remember, it's not just mobility which matters here. What matters is the amount of time it takes for a carrier to go from one to the next place here. These films are very thin. I have 50 nanometer films. I have 100 nanometer films. They're very, very thin films, so I don't require very high mobility. So even though the mobility is 10 to the power minus 4 or 10 to the power minus 5, they can switch at megahertz speeds. Organic LEDs. Okay. And remember, for a display, I need to switch the LEDs, right? On and off. Because if I'm making an LED. But remember, how often do you have to switch? See, this is a bias that we carry. I need very high mobility. For example, if you're using an LED in a display, right? How fast do you think you have to switch? Now, you know that displays are like matrix. And some of you know from your early CRT, so you go and display first row and then the second row and the third row and all that, right? So, and then you display the whole frame. And after you display a whole frame, then you go back to the first row. Now, what is the frame rate that you're familiar with? 24? or 50 hertz or 100 hertz, something like that. So once you switch an LED on, and then after how much time do you have to come back and switch it off? It's like 100 hertz. You don't require very high speeds, right? You don't require for here. If you're using an LED for lighting, lights, they don't have to switch at all. Okay, once you turn them on, right? It doesn't matter. Solar cells don't switch at all, right? Of course, but once you shine a photon electron hole pairs, they have to go to the electrodes and all that, and in the process they can recombine. Okay, so you need high mobility, but you don't require very high mobility. Along with mobility, other things come into picture. If you can make recombination less, if you can make the films thin, you can get viable devices. As I said, 10% solar cells with 10 per minus 3 mobility. Very efficient organic LEDs at 10 per minus 5 mobility. Okay, the place where you need really mobility is in a transistor. If I have a mobility which is low, my transistor switching speed will be low. Okay, so that's the place where is extremely important here. But then I have many applications. Suppose I'm making a temperature sensor, right? I'm making a temperature sensor. Now it has to sense the temperature, and then the value that you get is some value, and then you want to convert it into analog value. You want to convert it into digital and all of that. Now, how much speed do you need for a temperature sensor? I mean, you take it out and you want to see a reading in a few seconds, would be fine. You take it out and so you don't require very high processing speed. So even if I have a transistor whose unity gain frequency is 1 kilohertz, right? FT that you talk about, unity gain frequency is 1 kilohertz. That's fine for many of the sensing applications. I don't need a gigahertz transistor for this. So my point is, mobilities are low. They will limit the number of the kind of applications that you can address, but there's a huge variety of applications which don't need those numbers that you think of. You don't need numbers of 1,000 mobility. You can do very well with 10 per minus 3, 10 per minus 4 with a mobility of 1. Okay. By the way, the mobility of organic materials don't think that it's only that much. People have even reported mobilities as high as 10 and 15. Of printed layers, mobility is as high as 10 and 15. But what I'm trying to say is you don't need it for many applications, that kind of mobility. Okay, small mobilities are also reasonable here. Another weakness of these particular materials is that they're pretty sensitive to oxygen and moisture. And therefore, stability is a problem. Right? And so for example, if I take a solar cell that we make in the lab, if I make this solar cell and keep it in the normal ambient, the solar cell will degrade in minutes or an hour. It will degrade. It will lose its performance because the material reacts with oxygen and moisture and degrades. And so the material is very sensitive. By the way, if you go back and read about silicon and others, they were also very sensitive. And so silicon ICs and all are encapsulated and covered, silicon dioxide and other things. So here also, people have solved these issues to a large extent by taking an organic material and then covering it, by sealing it. After you make the whole thing, you seal it so that you prevent oxygen and moisture reaching your active layer here. So you have to do that, and then people have achieved lifetimes in 5,000 hours, 10,000 hours, that kind of a number. Organic LED will not be in your cell phone if it was going to degrade in a few months, right? So active matrix OLED phones are there, which means that they're going to last for a few years. Okay, so that problem is there, but it can be handled. It can be managed. Okay. All right. So that's so you are seeing the. By the way, poor electron and hole mobility I'm mentioning, but people have demonstrated. All of you may have heard of RFIDs, and one of the standards for RFID is 13.56 megahertz. People have made RFIDs using organic materials which can operate at that frequency, at 13 megahertz. So you can reach speeds of megahertz as well. Okay, but then with many of the circuits that you'll make, even if they switch at few hertz, it's fine. You can make applications out of it. All right. So let me come to now just highlight a couple of important applications here. A couple of companies, Philips and others, they talk about a concept of ambient intelligence, which is basically a new era of integrated electronics, where electronics is pervasive and unobtrusive, meaning that you can embed electronics in your surrounding. As I said, you can embed electronics in cloth, you can embed it in paper, you can embed it anywhere that you like here. So in some sense, then you can make your entire ambience which is there intelligent. That's by intelligence, what they mean is embedding electronics into it. Okay, so they talk about this particular concept here. Let me give an example here. You can look at that. You can see this. I'll not play the whole thing here. So you can see this YouTube video later on. This is on called Smart Window. Okay, Smart Window. And so this, you can see here, displays and electronics is embedded in this particular window here. Maybe I can. I don't have much time, so you can just. Okay. All right, so let me stop it. So you have all this display and all electronics here, and you can put anything in. Okay. The whole basket of applications here, displays, scanners, X-ray imaging, photovoltaics here. Let me show you. These are examples of different displays. Displays which are already there. You can. This was a Kodak camera. So this is an OLED display here. As I said, in cell phones you already have TVs are already there. This is a display from Sony that you can wear. This I've put because of his this display is there in an electronic shaver, and his claim to fame is that it was used by James Bond in one of the movies. James Bond used these organic displays in one of the movies here. All right, but so you may be wondering here. Well, I can put an LCD also in all of these places. In a shaver, you see an organic display. What's so big? I can put a LCD display, which I'm familiar with. I can put an LCD here also. LCD has been there at all these places here, and all of that you're familiar with. So this is the trouble. When a new technology comes in, now it faces something is already there in the market. In our case, the LCD is a well-entrenched display. It's been there for 30, 40 years. It started in 70s. So this is a well-entrenched technology. So when people come up with a new technology for displays, what do they think? The first thing that comes into mind, wherever LCD is, let me replace it. Right? So you take the LCD out and put it there. That's how it starts. But then later on, so when you go back and see when people came up with transistors, right? What did they do? Well, wherever vacuum tube is there, let me take the vacuum tube out, put the transistor there. That's all that they could think. But remember, at that particular point of time, it was very difficult to think that the transistor and IC would enable a cell phone. There was no cell phone at that particular point of time, right? Or a laptop or a cell phone. So it's very hard to think. But eventually, the value of a transistor or an IC is not that it replaced the vacuum tube, right? In the applications which it existed. In fact, it enabled a whole new set of applications. With the transistor and IC came a whole new set of applications which were not possible with the vacuum tubes at all. That's so similarly, organic LEDs have come. Right now, what people are thinking is, well, let me replace it here wherever LCDs are there. But eventually, this is something interesting that this person, again, another Nobel laureate, said, that the principal applications of any sufficiently new and innovative technology always have been and will continue to be applications that are created by the technology. It's not just replacement here. Eventually, if organic LEDs have to succeed, it will not come through by only replacement. It will come by creating new applications which LCDs cannot do. Okay, and some of the things that people have been talking about are, for example, a flexible display that you see here, made on plastic, and this will give you more a better view of the advantages here. So this is why flexible displays. Well, let's see this video. So that's the display here. So it's extremely thin. You can bend it. Maybe first time it was not hit hard. I think second time. All right, so that tells you what you can do with these plastic displays, what advantages plastic displays will have. Oops. Okay. Here are some more. So this looks like a pen. So that's a rollable display. You can roll it up, carry it in your pocket. All right. So, and you know, you can see many other things like this here. So, so displays is one of the major applications of organic LEDs. Of course, it's a big market already. The other one, upcoming market is lighting. So that's sort of a history of lighting that you see here, from fire to candle and all that. And all of you know that LEDs are coming in a big way. And the advantages of LEDs are shown over here with respect to bulb and tube light. The advantage is in lifetime. The LEDs are very, very reliable, 50,000 hours or 100,000 hours. So the idea is once you put an LED based bulb is going to be there for your lifetime, right? So the lifetime is very, very high. Efficiency of LEDs used to be low, but then they've already crossed beyond tube lights. They're more efficient than tube lights. I'm talking about inorganic LEDs, more efficient than tube lights. The problem has been the cost. Cost has been high, but the costs have been coming down very rapidly. Okay. Now this is where organic LED comes into picture. As I showed you, the costs of making organic LED can be much smaller by using printing and other techniques here. So it can really bring the cost down. Organic LEDs efficiencies have already exceeded. They've already exceeded this 80 lumens per watt. They're also more efficient than the tube light, at least in laboratory. Okay, and costs are also coming down. Right now, the costs are high, and so another place where organic LEDs are going to make their mark is in the field of lighting. Okay. The other advantage is, you see, conventional LEDs are point sources, so you have to take many of them, and what you have to do is you have to add optics to it to make it a broad source here. Organic LED, on the other hand, you can print it as a broad source directly. Okay, so you can make these broad diffuse sources, and you can have all these panels which are lighting panels, unlike inorganic LED, where you have to take a point source and then add optics to spread the light, and all those complications are there. None of those are here. You can just print this wide area source which emits light here. All right. Organic transistors. As I said, the organic transistors you can print on cloth, you can print on paper, you can print on any of these substrates here, and the applications are they are slowly emerging. These applications, for example, e-textiles here, electronics integrated directly on the. There's a big push towards all these wearable things that you can do health monitoring and all of that. Right now, they are being done. Some of these are being done through inorganic electronics, where you do that. But eventually, if electronics has to be integrated into the fabric itself, then organic may be the route to it. I'll give you another example of this RFIDs. They have been there for a long time. The traditional way of making RFID is that you have a printed antenna and you have a silicon RFID chip. And what you need to do is you have to take this silicon silicon chip here, put it on the piece of plastic, let's say, on which antenna is printed, and then interconnect them to make a complete this RFID here. Now, again, this is a discrete way of making RFID because you have to separately make the silicon IC, bring it to the substrate, stick it, and interconnect it to the antenna here. Now, the idea is that if I can make the whole thing monolithically in the sense print the antenna, print the IC and everything on it, the cost of the RFID may come down drastically. And therefore, it can be, it becomes so cheap that I can put it on medicine bottles, potato chips, and all sorts of places. Wherever you see a barcode, maybe you can put an RFID. So that helps in tracking and gives you a lot more for inventory control and all of that. So the idea is that if you can print transistors which can work at, let's say, 13.56 megahertz, and thereby make very cheap RFID here, RFID here. This is an example of a transistor printed on a sheet of paper. You can see gate here, insulator, gate, insulator, and then two electrodes which are here, source and drain, and this is the semiconductor here. So these are inverted. Gate is at the top, bottom here, and you have not a very nice transistor, but you can clearly see drain current versus drain voltage here. And this is an example of an early transistor here. Okay, so what it is opening up is disposable electronics. You have all these things which are printed on. It's just like a newspaper printed on a sheet of paper. It's very cheap. Use it, throw it. I don't know whether it's good environmentally, whether it's good or not. But the point that is that you can make it ultra cheap. Okay. This is again talking about an organic TFT on fiber. And let me, okay, so that's on transistors. Let me come to solar cells. We all, I don't have to go through, we all appreciate the need for solar cell, directly converting solar energy into electricity here. One of the major problems has been that the costs have been high, although in recent, last 2-3 years, the costs have really come down. And if you examine the cost of a silicon solar cell, this shows you a large percentage of the cost comes about because of the silicon wafer. The silicon itself is very costly here. And then the other part comes from processing, making the solar cell. And then another fraction comes from taking solar cells and then, again, it's a discrete way of making a panel. You make a solar cell separately and then you bring all these solar cells on a big piece of glass and you put all these solar cells and you interconnect them in series and parallel and make a module, right? So now the idea is that, I could use printing to print my solar cells here and on plastic. So my substrate is very cheap, or on paper. So unlike silicon substrate, which is expensive, I'm now making my solar cells on plastic or glass or plastic or paper, which is very cheap. So substrate is very cheap. My processing technology, which is printing, that's very cheap, right? And not only that, I don't have to make separate small solar cells and then put them on glass. I can make the module directly on a roll of plastic here. So this is what you see here. So the idea is that maybe my efficiency may be low, may not be as high as this thing. But remember, for solar cell, what matters is not the efficiency, but what matters is what you see here. How many dollars or how many rupees you have to pay for 1 unit of electricity. That's what matters. It's not the efficiency. It's ultimately what you're paying for 1 unit of electricity. So you can imagine that I can have a solar cell which is, let's say, not very efficient, right? But it's very cheap. And therefore, its cost may be low. The cost of generating electricity through that particular route may be low. So that's the motivation for people working with, with the organic solar cells. One is to make it cheap. And the other thing is it's flexible and you can put it on anything. You can put it on windows. You have a film and you can stick it to the windows, right? And another interesting thing that this is what you see is here. And you can see here how organic solar cells are being printed here on a roll to roll. The whole thing is a It's like a panel here. So roll-to-roll printing for organic solar. So that's the idea. The other thing is very interesting that people have taken organic materials which are partly transparent, and they've made solar cells out of it on pieces of plastic with efficiencies of around 6 or 7%. Right? As I said, typical commercial solar cells would have efficiency of 15 or 18%. So that's high. But then they've made partially transparent. So you have an organic material which will absorb in the infrared region here, leave a lot of visible light to come in. And so you have a transparent solar cell, right, on a piece of plastic. So what you can do is you can stick it on the window, and it's transparent. It allows the light also to come in. At the same time, it's generating electricity also. It's a solar cell which is there, which is generating. So transparent solar cells. Okay. So that is there. Yeah, this is also interesting. Look at this solar cell here, made on a piece of paper. So he has a ammeter here, and he's trying to show. So look at, you have a solar cell on paper. You can bend it, fold it, and make an aeroplane out of it, and then he'll connect it and show. There. Right. So paper solar cells. Connect it up. Well, you can see the current when it's off, 0.01. When the light is on, 0.45. So it's demonstrating two things. One is a working solar cell on a piece of paper. And the other thing is you can take it, fold it, bend it, all these things you can do, maybe crumple it, keep it in your pocket and then take it out. It still works. It still works here. Okay. All right. I'll stop with this one. A few names, important contributors to this particular field here. This field of organic electronics has been, people have been working for a long time, since 1960s and all that. They've been working slowly on organic semiconductors here. But it got a big boost. This whole field got a big boost when Nobel Prize in Chemistry was given in 2000 for work on conductive polymers. These are the three people, Heeger, McDermott, and Shirakawa. Before that, when you think of plastics, the thing that comes to your mind is an insulator, right? Plastics are insulators everywhere around your, cups. This is what you're familiar with. If you attach electrodes to it, it doesn't conduct. It's an insulator. Okay. These people, their work, they showed that you can make plastics. This is mind-boggling, that you can make plastics as conducting as metals. Look at that. This is a chart that you may have seen here, which shows conductivity, right? You have all these insulators here. You have all these metals, right? Very good metals, silver, copper, and all that. And here is an example of a polymer with some doping that gives you conductivity right here. So a polymer now gives you conductivity just like metal, right? So now you can imagine polymers were all along thought of as insulators, and their work showed that, well, by doping and by some means, I can make my polymer as conducting as a metal. So you can have a polymer, means a plastic. So you can have a sheet of plastic which is as conducting as a metal. So that was a huge thing. And of course, polymers are insulators, that we well know. So now they're conductors also. They're like metals also. So in between, then they are as semiconductors also. So polymers now can be insulators, they can be semiconductors, and they can be metals. So you can imagine what do you need to make any electronics? You need metals, insulators, semiconductors. Everything is there in polymer. And then polymers you can dissolve in a liquid, right? So you can imagine now I can make an all polymer IC, all polymer transistor, all polymer IC, all these things then open up here. Okay. The other major contributor was this particular person, C.W. Tang at Kodak. As I said, organic LEDs people had been working on since 1960s. They were getting very low efficiency. His work, he made a fairly efficient organic LED, showed a way of doing it in around 1987. And two things he did. So people had been working on organic solar cells also. They were not very efficient. And he showed a efficient organic LED and an efficient photovoltaic cell. Both of that he showed through his work at the Kodak here. And in some sense, the modern organic electronics was launched through his work. Organic LEDs and both solar cells. Okay. And this was, so he used a material which is what we call a small organic molecules. This person, Richard Friend, he showed that polymers can also give rise to light here. So his work showed emission of light through polymers here. So polymer LED by Richard Friend here.